In this episode, we ease into one of the most important everyday security ideas in Linux, which is that control over a system often begins with control over files and directories. When people first learn Linux, they usually notice that everything is a file in some way, but it takes longer to realize what that really implies for security and reliability. Programs, configuration, logs, devices, and even many parts of process behavior are governed by files and the permissions wrapped around them. That means a small misunderstanding about who can read, write, or execute something can turn into a big problem, like a service failing to start, a user seeing data they should not see, or a malicious change that goes unnoticed. The good news is that Linux permissions are consistent, and once you understand the model, you can reason about it calmly instead of memorizing exceptions. We are going to build that model step by step by connecting the classic permissions tools like chmod and chown to special bits, umask defaults, access control lists, ACLs, and file attributes, so you can see how all these pieces fit together. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. The foundation is the idea that every file and directory has an owner user and an owner group, and those identities anchor the simplest permission checks. The system evaluates what you are allowed to do by asking whether you are the owner, whether you are in the owning group, or whether you are neither and therefore treated as other. For each of those categories, Linux tracks 3 basic permissions: read, write, and execute. Read generally controls whether you can view the contents of a file or list the names within a directory. Write generally controls whether you can change the contents of a file or create and remove entries in a directory. Execute is the one that surprises beginners, because on a file it controls whether you can run it as a program, but on a directory it controls whether you can traverse into it and access items inside, if you already know their names. That directory meaning is the reason you can sometimes list a directory but still get blocked from opening files inside, or the opposite, where you can access a known path but cannot list the directory contents. Chmod is the tool most learners meet first, and the important thing is not the tool name, but the concept that permissions can be represented both symbolically and numerically. Symbolic changes are often described in terms of adding or removing read, write, and execute for user, group, or other. Numeric representation compresses the same information into a set of digits, where each digit represents a category and each bit represents a permission. You do not need to become a math expert, but you do need to know that the digits are not arbitrary, because they map to a simple pattern that makes it easy to read and easy to audit. The reason this matters for Linux Plus is that exam questions often test whether you can interpret permissions or predict the effect of a change without needing to see a live system. The deeper reason it matters is that permissions are a form of policy, and being able to read them quickly lets you spot unsafe settings, like world-writable configuration or overly restrictive settings that will break a service. Chown is the companion concept, because permissions depend on ownership, and sometimes the simplest fix is not changing the permission bits, but changing the owner or group to match the intended responsibility. Ownership answers the question of who is supposed to be accountable for the file and who should have the primary ability to change it. Group ownership answers the question of which team or role is supposed to share access, which is common for collaborative workflows and for services that need shared directories. Beginners often try to solve everything with chmod, but that can lead to overly permissive settings because they are using broad permissions to compensate for incorrect ownership. A more disciplined approach is to think in terms of intent: who should own it, which group should share it, and then what minimum permissions are needed for that owner and that group to do the job. When you approach it that way, you often keep the other category very limited, which reduces accidental exposure. Once you are comfortable with basic permissions, the next idea is that Linux includes a few special bits that change how permissions behave in specific high-impact cases. The most famous is the setchmod bit, which causes an executable to run with the privileges of the file owner rather than the privileges of the user who launched it. The setchmod bit is similar, but it focuses on group identity, and it can apply to executables into directories in a way that supports shared collaboration. There is also the sticky bit, which is most commonly used on shared directories to prevent users from deleting or renaming files they do not own, even if the directory itself is writable. These special bits exist because the basic model is sometimes not expressive enough for real needs, but they are also dangerous if misunderstood because they can become privilege escalation paths or allow unexpected sharing. The practical takeaway is not to fear them, but to treat them as deliberate exceptions that should have a clear purpose and should be audited, because they change normal expectations about who can do what. The Setuid concept often feels abstract, so it helps to focus on why it exists in the first place. Some operations require elevated privileges, but you do not want users to have full root access just to perform one safe, bounded action. A carefully designed program can run with elevated privileges long enough to do a specific task, such as modifying a protected system setting, and then exit, ideally without giving the user general control. In other words, Setuid can be a controlled bridge, but only if the program is written to be safe and to avoid being tricked into doing something unintended. That is why Setuid programs are a security focus, because if a Setuid program has a flaw, it can be abused to gain broader privileges. From a Linux Plus perspective, the important understanding is that Setuid and Setgid change the identity a program runs as, and that identity change is one of the most powerful things you can do on a system. Directory-level Setgid is a particularly useful idea for shared work because it changes how new files and directories inherit group ownership. In a collaborative directory, you may want every new file created there to belong to the same group, so team members can access each other's work without constantly changing group ownership manually. The Setgid bit on the directory helps enforce that policy by making new entries inherit the directory's group rather than the creator's primary group. This reduces friction, but it also means you must think carefully about who belongs to that group, because group membership becomes the gate to shared content. It also means that write permissions on that directory become more significant, because being able to create or modify files in a shared directory can influence what others see or use. This is one of those areas where permissions connect directly to system integrity, because a malicious or careless change in a shared location can impact other users or services. Understanding the inheritance behavior makes it easier to predict who will be able to read and modify what, which prevents both outages and accidental data leaks. Umask is the next piece, and it exists because permissions are not only changed after a file is created, they are also set at creation time based on defaults. When a process creates a new file or directory, it starts from a maximum set of permissions that makes sense for that object type, and then subtracts permissions based on the umasked value. The easiest way to think about it is that umask defines which permissions are not granted by default, which is a safer framing than thinking of it as adding permissions. This matters because many security problems come from unsafe defaults that nobody notices until data is already exposed, especially when programs create files automatically, like logs or temporary files. If your umask is too permissive, you can end up with files that are readable or writable by more people than you intended. If it is too restrictive, programs may fail because they cannot share needed files with a service account or a group. The skill is to see umask as the default policy for new objects and to align it with the environment's expectations. The classic permission model of user, group, and other is powerful, but it can be limiting when you need more precise sharing. And that is where access control lists, ACLs, come in. ACLs let you grant permissions to additional specific users or groups beyond the single owning user and owning group. This is useful when you want to share one directory with a particular user without changing group membership, or when you want a service account to have access to a file owned by a different user without making it world readable. The key beginner idea is that ACLs extend the permission model, they do not replace it, and the base permissions still matter. That means you can create confusing situations if you rely on ACLs without understanding how they interact with the existing bits, because the effective permission is a combination of base permissions and ACL entries. In troubleshooting, one of the most common surprises is that a file looks locked down based on its normal permission string, but an ACL grants additional access, which is why security-minded admins consider ACL review part of auditing. Default ACLs add another layer, because they influence permissions for newly created files and directories within a directory, similar to how a mask influences creation. If you have a shared directory where multiple roles need consistent access, default ACLs can ensure that new files inherit the correct access permissions automatically. This reduces manual fixes and reduces the temptation to set overly broad basic permissions just to make sharing work. At the same time, default ACLs can also create invisible complexity for beginners because the permissions someone gets may be coming from inheritance rules they cannot see at a glance. The practical approach is to treat default ACLs as a deliberate policy tool for shared areas and to document that policy so the next person understands why permissions behave the way they do. In exam terms, you want to recognize that ACLs exist to provide more granular permission control than the classic model. File attributes are the final piece in this episode's theme of control, and they matter because they can restrict or protect files in ways that normal permissions do not capture. Attributes can include flags that make a file harder to change, harder to delete, or treated in a special way by the system. A beginner-friendly way to think about attributes is that permissions answer who can do what, while attributes can answer whether the system will allow the file to be changed in general, even by a privileged user, depending on the flag and the file system. This is often used as an extra safeguard for critical configuration or logs, where you want to prevent accidental modification or tampering. It is also useful when you want to preserve integrity in the face of automation scripts that might otherwise overwrite something. The important caution is that attributes can also confuse troubleshooting, because a user might have write permission but still fail to modify a file due to an attribute restriction. So knowing that attributes exist prevents you from assuming permissions are the only possible cause. When you tie these ideas together, you get a clear picture of how Linux expresses and enforces control over data and behavior. Chmod adjusts the core permission bits, chown aligns ownership with responsibility, and special bits change how identity and deletion rights behave in high-impact cases. Umask shapes safe defaults at creation time, so you do not depend on manual corrections after the fact. ACLs extend the basic model when you need precise sharing without broadening access for everyone, and default ACLs let that precision carry forward automatically in a controlled directory. File attributes add a last line of defense by placing extra restrictions on modification or deletion, which can support integrity and auditing. If you keep the model in mind, you can diagnose most permission problems by asking a consistent set of questions about identity, ownership, base permissions, special bits, inherited defaults, and any additional access layers. That structured thinking is what the exam rewards, and it is also what makes Linux feel like a system you can reason about rather than a system you have to memorize.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.